the inclusion-exclusion principle. We saw the inclusion-exclusion principle for 2 sets, and now we'll do it for 3 sets. So here's our little Venn diagram. Let us take some general sets A, B, and C, and we want to count what is the union of these things. What is the size of the union? And if I tell you that, well, this is what we want, A, union B, union C, I want to count the size of this thing. Well, the first thing I might do is say, well, it's all of A, so that's size of A, plus all of B, plus all of C. I need my pencil. But of course I've counted too much here. I've counted the overlaps extra times, just like before. This region here, between A and B, that's been double counted. Because I counted it once when I counted A, and I counted it a second time when I counted B. So I need to remove that. I need to remove the intersection A intersect B. And this stuff down here, this stuff between the intersection of B and C, well, I counted that twice. I counted it once for B and once for C. So I need to remove that intersection to balance it out. That's B intersects C. And then finally this section over here, between C and A, I counted that twice, once for A, once for C. So I need to remove that as well. And then you say, oh no, Daniel, wait, hold up, dude. That stuff in the middle has now been removed 3 times. This stuff. Can't see it. This stuff. This kind of triangular-like region in the middle. You removed that 3 times. I mean, you counted it 3 times, once for A, once for B, once for C. And then you removed it 3 times, once here, and once here. So this statement, as it stands, is incomplete because you haven't counted that middle region. And so we just add it back in. There you go, middle region. Behold, the inclusion-exclusion principle applied to 3 sets. Now you can hopefully you have enough understanding now to just derive this formula if and when you need it. So let's do this example. You might have seen questions like this already. Is this like something they ask in high school? Is this a thing? Yeah, you see Venn diagrams in high school. Sure. I mean, you can straight up just apply the inclusion and exclusion principle, or you could do it just using the pictures. I kind of like doing it both. Okay, let us read of the question together. In a class of 40 people studying music. Okay, so that tells us that the set S. Let S be equal to the best way to start your questions about probability and counting is to define the universe. That's the first thing you do, always. This is what I'm talking about. You don't just start rattling on, I'm talking about people playing violin. No, you're talking about people in a particular music class who also play violin. So you start off by defining your universe. And then the other stuff. 2 people play violin and piano and recorder, so I'm going to define some variables here that violin, piano, and recorder be equal to. Violin, and then this thing can just be same stuff but with piano, and this can be same stuff but with recorder. Good. Then we know some things. Let's just read out the question now. We've defined some variables so we can translate this bunch of words into statements about the size of these sets. Then I know the size of S, that's equal to 40. The size of, let's see, 2 play violin, piano, and recorder. That's V intersect P intersect R, and that's 2. I know 7 play at least violin and piano. So violin and piano is 7. 6 play at least piano and recorder. So that's piano and recorder is equal to 6. 5 play at least recorder and violin. So recorder and violin is 5. 17 play at least violin. 19 play at least piano. And 14 play at least recorder. How many play none? Oh. So we're actually interested in this region. The region outside the worlds of recorders, violins, and pianos. Well, let's do some things here. This can be my violin world. This can be piano world, and this can be recorder world down here. Now you can at this point just straight up apply the formula, and great, you're welcome to do that, and maybe we should do that. But I'm going to pursue this a slightly different way, slightly I think more visual way. And that is, you start from the middle. So I know the size of the middle. I know that's 2. So this region in here, that's got that's got 2 people in it. And then violin intersect piano. That's got 7 people. 2 of them are in this intersection over here, and the remaining 5 are over here. 6 people are in the intersection of piano and recorder. So that's this intersection. This whole intersection contains 6. 2 of them are here. That means 4 of them are here. Recorder intersect violin, that's this region, contains 5 people. 2 in this triple intersection area over here, which means there's 3 people over here. Good. Now let's talk about the people who exclusively play the violin. 17 people exclusively play violin. Sorry, 17 people play violin, and 10 people of those 17 play extra instruments. So 5 plus 2 plus 3, which means 7 people are over here playing exclusively violin, making up 17 in total. Piano, well, let's have a look at you, piano. 11 people in here play other instruments, including piano. 19 play piano, which means 8 play exclusively the piano. This total here making up the 19. And then finally down here, 9 people in the intersection. 14 people play recorder, which means 5 people down here. And in this way, you can just say, oh, well, how many people are in this this area, this region here? Well, you just add all this stuff up. So that's 17 plus 15 is 32. So it's 34? I believe you. Really? 17 plus 17. There you go. Awesome. 34 people are in this union, and so in this area, in these circles here, it contains 34 people. There were 40 people in the class though. Is the size of V union P union R, I guess, complement. So here's the people who play one of those, at least one of those instruments, and we want to know how many people are not playing at least one of those instruments, which is the set complement, and this is the size of the universal set minus the size of V union P union R, which is 40 minus 34, which is 6. Okay. Maybe I should mention, I applied the inclusion-exclusion principle in this kind of visual way. I encourage you to do that. That's a nice way of doing it. But you can also just straight up apply the formula. Note that B union P union R is equal to, just apply the formula. 17 plus 19 plus 14 minus the intersections plus 2. It's 34. So you could have done it just by straight up applying the formula. I kind of like the visual way of doing it. Up to you how you want to do it. Good. We have now learned a little bit about counting. And really the only thing that is perhaps new is the inclusion-exclusion principle and the language around sets. Let's talk about probability. We use the word experiment to describe the recording of an observation, measuring something that happens. You might like to say getting coins, tossing coins would be an experiment. Now I can toss the coins, and what are the possible outcomes of this experiment? You can get double heads, you can get heads tail, you can get tail head, or you can get tail tail. 4 possible outcomes of the experiment. Now the thing that really interests me, and the thing that made me stop playing poker, is that you don't know. Actually, let me just finish this first. The set of all possible outcomes in a given experiment is called the sample space, and we denote it with S. So remember that universe? Remember that population or world of things that we were considering? That's the sample space. And an outcome is an individual outcome is an element of the sample space. And do I have an event here? Yes. So let me just give you an example. When you when a coin is tossed 3 times, and the outcome is given as a sequence of head and tails, the possible sequence of objects could be, well, it could be head the first time, head the second time, head the third time. Triple head. And an element of a outcome of this experiment might be head, head, head. But you can also have head, head, tail, or head, tail, head, or head, tail, tail, or tail, head, head, or tail, head, tail, or tail, tail, head, or tail, tail, tail. Behold the world of possible outcomes of this experiment. So when we're talking about coin tossing, this is tossing a coin 3 times. This is what can possibly happen. Each of these individual things is an outcome. So if I take my coin and I go once, head, twice, tail, tail, head, tail, tail, that thing actually occurred in my kind of implementation of that experiment. And that is an outcome. When we perform the experiment, we are often interested in not just one outcome, but a whole perhaps range of outcomes. You might want to talk about the outcomes where there's an even number of tails, or the outcomes where there's all heads or all tails. And that collection is called an event. And events are typically what we're interested in. They're subsets, not individual elements, but subsets of this space. If you're talking about people in Sydney, you might want to talk about the subset of people who are students at UNSW. That would be considered an event. You don't necessarily care about the individual people, you care about groups of people. And that's what you want to talk about. Two events are said to be exclusive when their intersection is zero, or is empty. Now, this is the thing that really interests me. I tossed a coin, right? The odds of it being heads, let's say 50%. Odds of it being tails, also 50%. Does that tell me what the outcome of my coin flipping is going to be? In what sense do I interpret this number? What does it mean? What does that number mean, saying it's 50-50? Yes, getting there. It's actually saying it's 50% chance of being heads. It does not refer to an individual coin flip. It refers to the long-term behavior. So probability doesn't tell you about what's going to happen in the next instance of this experiment. You could flip all tails. It tells you about the long-term behavior of the experiments. So the fact that you know, say, the coin is going to be heads with percent, maybe even 90%, it doesn't tell you that the next coin flip is going to be 90%. And if it's tails, then that's just how it is. What it tells you about is the long-term behavior. So the theory of probability is a fact about the regularity of random events. It means that in a large number of trials, the relative frequencies of these outcomes will stabilize. So not individual outcomes, but the long-term behavior of infinitely many outcomes. So it's really a statement about the limiting behavior, not the individual outcomes. Of course, the interesting thing, and the only thing we can do is determine the limiting outcomes and reason about the long-term behavior of something. And it's a very powerful thing to do. If you want to gamble, then you want to know what is going to happen in the long term. Right? In the individual outcomes can, sometimes you get lucky, sometimes you don't. But what is the long-term behavior here? So, say for example, we toss a coin repeatedly and we keep record of the number of outcomes. You toss the coin 10 times, you get 3 heads, and the proportion of heads is this much. You toss it 30 times, you get 14 heads, it's this much. 50 times, 26 heads, it's this much. And slowly, it starts off below 50%, above 50%, below, and so on. The idea is that sometimes the coin favors heads, sometimes it favors tails, and in the long run, it goes to 50%. So if it's a fair coin, then as we would expect on average, then we get roughly the same number of heads appearing as tails, and we say the outcomes are equally likely. To talk about more sophisticated things, we need a bit more language. Suppose you have a sample space. Suppose, if you like, it's this sample space here, if we want to be explicit. And A is an event in S, that is, it's a subset of S. Maybe it's the set of events that contain at least one tail. Then the probability of A, it is denoted by P of A, so it's the P of A, is a number. P of A, it's a probability required that P maps events, events, the worlds of things we're trying to measure, into numbers, typically between 1 and 0. So P is a map from events into the numbers 0 to 1. And roughly speaking, P measures the likelihood of something occurring. So it's a number between 0 and 1 for every subset of the sample space. P of something that is empty is 0. If you say, what is the probability of none of the events? Let's return to this. If I want to know what is the probability that none of these things are going to occur, probability function. I'm going to flip my coin 3 times. What is the probability that nothing happens? And the probability function says 0, meaning something is the probability that nothing occurs is 0. Something is going to occur. So this 0 here means that not. It's literally telling you it's not going to happen. Probability of 1. Probability of S itself. So the probability of S. This is like asking my probability function. Function, what is the probability that in my flipping of a coin 3 times, one of these things is going to happen? And the function tells you, well, that's the set of all possible things that can happen. So that's going to happen absolutely, certainly. It's going to happen, sure thing. So this is the sure thing. If you've ever played poker and you've got yourself a royal flush, you are going to win that hand, sure thing. 100% every time. Your hand is unbeatable. So that's only ever happened to me twice. In both occasions, I've been accused of cheating. But you absolutely clean up if you play it right. By the way, you can't just, if you get a royal flush, you can't just go all in. You'll scare everyone away. You need to convince them that you don't have a royal flush, and then hit them with the royal flush. They won't like it either way you play. Any way you play it, it never goes down well. If A and B are mutually exclusive events, then the probability of A or B occurring is the probability that A occurs or the probability that B occurs. So to be very explicit about this, if we let A be the set H, 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 and B be the set tail, tail, tail. So if A is the set all heads, B is the set all tails, these things are mutually exclusive in our lingo. Perhaps you've used it already. Probability of A or B occurring is probability that A occurs plus the probability that B occurs. Given these two things don't actually overlap. Now, in a finite sample space with equally likely outcomes, such as our coin flipping example, since the sum of all probabilities is 1 and there are S elements altogether, then the probability of each outcome is necessarily 1 on S. And applying this rule, we have this. So we can say, or we can do a few examples. We'll do a few examples in a moment. So, the real question is, practically speaking, how do you assign probabilities to things? I mean, most of the time, in this course, you're just going to get given the probability function, and you're going to be told, here is the function. Just do some manipulation with the function. In reality, though, you need to come up with this function, and how do you do that? Well, analysis of symmetries is one way to do it, but it requires requires actually symmetric outcomes. The results of large data collections, that's what you will end up using most of the time. You'll actually have, the first step you'll do is actually gather data, figure out what this probability function is, and then go off and use it. Use of an expert opinion, that's a cop-out as far as I'm concerned. It's just asking someone else to do this or this. So, okay. Example. Suppose you have a 12-sided dice whose faces are numbered 1 to 12. Assuming the outcomes are equally likely, what is the probability that a prime number appears on the uppermost face? Okay, so your task here, and the task is always the same. You have a bunch of words. Words are no good to you. You don't want the words. You can't do algebraic manipulation with words. You need to convert your words into the language of sets, and then from sets into the language of probability. Sets are always the intermediate step, though. That's how you get words into probability, is by first using the language of sets. Outcomes of your 12-sided dice, which is behold the universe. We are considering only these objects. And let us talk about P being outcomes which are prime. These being 2, 3, 5, 7, 11. Notice you do not include 1. 1 is not prime. Why? Why is that, by the way?
Because 1 is divided by itself and 1. Or
Yeah.
1 is already itself. Therefore, it's not prime.
But what does prime mean?
It can be divided by itself and 1.
But it wouldn't 1 being divided by 1 is divisible by itself and 1.
Yeah, but that's only one condition.
You need to have 2 different things. Yeah, the idea of primality is to take numbers and split them into different bits. So saying it's divisible by itself and itself is not really breaking it and making it composite, like a 6, which you can break into a 2 and a 3. So yeah, that's why you exclude 1, because you can't break 1. Not into integers. You can't. It's not composite. It's not made of 2 other things. So yeah, you don't include 1. 1's not prime. Then good. Then assuming all then. Then assuming all outcomes are equally likely, the probability of, I shouldn't have called it P, too bad. Can I call it A? I'll call it A, just to distinguish that P from that one. Yeah. So since all outcomes are equally likely, we just employ this counting procedure, which is going to be the size of A over the size of the sample space, which is 1, 2, 3, 4, 5. Over 12. The probability that the dice roll is prime is 5/12. This kind of procedure of counting is literally most of the subject. You count. That's all there is to it. And then you take this, you create this probability function by saying how many of the outcomes there are, and divided by how many of the outcomes there possibly could have been. So in this case, 5 prime outcomes 12 possible outcomes, the answer is 5/12. This looks familiar. And it's literally the inclusion-exclusion principle just scaled down by the size of the sample space. So that inclusion-exclusion principle, sure, exactly the same thing applies for probabilities. Because probabilities are just make statements about sizes of sets. Perhaps I'll say this is A union B. So this statement here, wrapped up in terms of probabilities, that was just the inclusion-exclusion principle in disguise. It was just the inclusion-exclusion principle divided by the size of the sample space. You can just treat them as the same thing, as far as I'm concerned. The probability of A complement is 1 minus the probability of A. And again, that's just the same statement that we had for sets, but wrapped up in terms of probabilities. Remember that the size of A complement was equal to the size of S minus the size of A. And if I divide everything by the size of S, then that's the probability of A complement is equal to 1 minus the probability of A. It's exactly, it looks the same. The statement about sets and the statement about probability looks exactly the same because it is exactly the same. And finally, if you have a subset, then the probability of A is less than or equal to the probability of B. Okay, and maybe, I suppose we would say A subset of B means that subset A or size of A is less than size of B, like that. Subset equal to. There we go. All right. Yeah, we don't need to do that. Examples. Oh, and mutually exclusive. Yeah, how interesting. All that intuition you have about Venn diagrams applied to sets, it works here, and it works here because these are really you can think about them as being sets. Fundamentally, they are just sets. So when you start with a question about probabilities, perhaps a good way to think about it is just with the Venn diagram, that you would think about it as a question about sets. Here's I'm told they're exclusive events, mutually exclusive, which means that B and A have no overlap. Over here, there's B. These probabilities here give me some kind of feeling of the relative size of A. So this region here, if you want to think about this as taking up, you can think about this as taking up, say, 48% of the space, which is a kind of nice way to think about 48%. And you can think about the probability of B as taking up 36% of the space. And the question asks you to do a few of these things. So A, the probability of A union B. Well, the probability of A union B is always the probability of A plus the probability of B minus the probability of A intersect B, just by the inclusion-exclusion principle. And we know the probability of A, that's 48%. We know the probability of B, 36%. And the intersection is 0%. So that's just equal to 84%. So together A or B cover up the whole space. The intersection, of course, A intersect B is straight up 0. The probability of A complement is 1 minus the probability of A, which is 1 minus 48%, which is 52%. 36%. And the probability of A intersects B complement. How interesting. How very interesting. I think the most appropriate thing to do in this case is to take A complement, which I'll do in green. Sorry? Yes, it would. But I want to give you a reason to believe that it's B. Like this. Here's A complement in green. And the intersection of A complement and B is just B. Oh, sorry, it's A. I've done it the wrong way around. Damn it! I'm changing the question so my answer is right. There we go. There you go. Don't try this at home. Okay, that's just the probability of B, which is 36%. Okay. Suppose we have a certain town where 80% of the population have comprehensive car policies. Okay. 60% have house cover and 10% have neither. This is my wife's kind of town. We should move to this town. She'd be very happy about it. So here can be one. I'll have, this can be car insurance. And this one over here, that can be, actually maybe I'll do it slightly differently. Let me do it a little bit differently. Sorry, I've messed up your page now, haven't I? Sorry about that. Okay. Here's my box. And we're going to say 80% of the population have comprehensive car insurance. I'm going to draw it like this. This grey shaded area. This is the comprehensive car insurance. Looks like that. As a percentage of the sample space, it should take up about 80% of the space. So you can draw it like that. Just over half of them have house insurance. So I'll go just a little bit north of half. And I'll draw it like this. How many of them have neither? And you can see based on just the way I've drawn it, it gives you some kind of visual representation of what's going on. This area here that is, and 10% have neither. That's the 10%. What percentage have both covers? So what is this? What is this intersection down here? What is the? I mean, you don't need to try and draw these percentages to scale, but if you have, but I think it does help a little bit. Okay, so here we go. That's the picture. We're going to let S be equal to the certain town. So population in a certain town, and we'll let C be that kind of car insurance, and we'll let H be equal to people with house then what do we get told? Well, we get told that a certain percentage, the probability, if you like, of C, can I write it as 8 over 10? The probability of H is 6 over 10, and the probability that you don't have either of these things, so that's the probability of the complement of C union H is that much. And I now want to know what the intersection is. So the probability of C intersect H. Well, using the inclusion-exclusion principle, that's just the probability of C plus the probability of H minus the probability of C union H. Just taking the inclusion-exclusion principle and swapping the roles of the union and the intersection. This I know, this I know, this I don't know. I don't know that. But I do know that since the probability of C union H is equal to 1 minus the probability of C union H complement, then that's 1 minus 1/10, which is 9/10. 90% of the people have some form of home or car insurance. Okay, that kind of makes sense. So now I know enough to make this inclusion-exclusion principle work. Equals 8/10 plus 6/10 minus 9/10, which is 5/10. Yeah, or 50% if you like. Okay. That's probably a good point to stop it before we get into counting techniques. Yeah, let's stop it there.